term be uncorrelated with the explanatory variables, right? That is really the basis of which we do a regression, right? Why is that the basis? Because the entire formula depends on that assumption, yeah? Right? So we basically did. So can I revise that quickly for some of you, so that I want you guys to have that idea very clearly, right? Okay? Sure? Why that's such an important assumption, and what happens if we quickly, and then we also actually saw some demos of that, right? We actually just looked at some simulations, but we'll actually see a demo of that. And then we'll start doing actual regressions in R and understand, right? Okay. So basically what I'm sharing my screen. Just to take a recap. Right, so you have y is equal to, this is visible? Y is equal to a plus bx plus e. This is the regression model, right? Where essentially we are looking at an individual specific term, right? So a plus bxi is the conditional mean, right? So the mean weight for a child who is x years of age, and ei is that child's individual specific heterogeneity. That's how we said you model a regression, right? So a plus bx tells you what is the mean, and the ei tells you the difference between that individual and the mean value of all those individuals. Yeah? Right? So if you, for example, have C is consumption, Ci is a plus by I plus ei. A plus by tells you the mean consumption of households which have income equal to y. And the ei tells you the gap between this household's consumption expenditure and the mean consumption expenditure of all households who have that income, right? By this logic then, the ei, which is specific to that household and reflects everything else but the income, because the income part is actually captured in the mean, the ei and the income, the error term and the income, or what is called the stochastic term and the income should be uncorrelated, right? Is this clear? Has everybody internalized this idea well enough? Yeah? Right? Okay. So then what we do is we simply find covariance of x with y is equal to covariance of x with a plus by plus e, right? Because y is a plus a plus bx plus e, right? Y is equal to a plus bx plus e. Sure? Okay? From which you have is equal to covariance of x with a plus b variance of x plus covariance of xe. Is this absolutely clear to everybody, this equation? And why is covariance of x with bx the same as the covariance at the mean to variance of x? Because covariance of x with itself is variance of x, right? And so we said that this first term is going to be 0 because a is a constant. Yeah? The last term is going to be 0 because x and e are uncorrelated. Sure? So what do we get? We get covariance of xy is equal to b variance of x, or b is equal to covariance of xy by variance of x, right? Right? And if you want to now do the, because you're going to do this on a sample, covariance of yx is going to be calculated from the sample, and variance of x is going to be calculated from the sample, and that's going to change from sample to sample. So you really write this as beta hat, right, is equal to sum x minus x bar into y minus y bar upon sum x minus x bar the whole square. You don't divide by n minus 1 because the numerator is divided by n minus 1, denominator is divided by n minus 1, so you don't really, right? So this is what the formula for u, right, for beta hat. Summation x minus x bar, y minus y bar upon summation xi minus x bar square. That comes from this logic. Yeah, you want to extend this to a bigger model. So you have y of bx plus say c star zi. Yeah. Then you will have one equation covariance of xy. Yeah. And another equation covariance of zy, right, is equal to covariance of z with a plus bx plus cz plus e, right? Okay. So the first equation gives you covariance of xy, right, is equal to, yeah? Okay, right. Thanks. Yeah? Right? Right, so if you just want to extend this, it will be B variance of Z, right, the first equation, plus C covariance of xz, right? Sure? And the next term will be covariance of, I think somebody else has come again. Admit all. Yeah, so next term will be, so B into, so next equation will be, so covariance of zy is equal to B covariance of xz plus C variance of z, right? Both the cases we use the assumption that covariance of x and e is 0, covariance of z and e is 0. And then covariance of xy can be calculated from the data, variance of z can be calculated from the data, covariance of xz can be calculated from the data. So you have three numbers and two unknowns. You have two equations and two unknowns, you solve them simultaneously. Yeah? Right? In fact, what your classroom will do is, they will say, okay, let me write B. They say, okay, let me write BC as a vector, column vector, right? Then they will say, okay, let me write covariance of xy, right? Okay. So what you write is covariance. So think of it this way. Covariance of xy and covariance of xz, one vector. 2 rows, 1 column. Right? Sure, 2 rows, 1 column. Right? And on this side, what you have? You have basically two terms, right? Okay, so look at this. B, variance of z, covariance of xz. Right? C, covariance of xz and C, variance of z. Right? So on the left hand side, you have covariance of zy, covariance of, covariance of xy, covariance of zy, one below another. Here you have B and C as a column vector, then a 2 by 2 matrix next to it, which will be what? covariance of xz, covariance of x, covariance of xz, covariance of xz, variance of z. Right? So if you call the first, I'm trying to imagine this, right? Because I don't have a blackboard to write it on, but a good idea would be to do that exercise. So think of this left hand side as a 2 cross 1 matrix, 2 rows, 1 column. What will be the first row? Covariance of yz, yx. Below that covariance of xz. ऐसा एक शेल्फ करके लेफ्ट में रख दिया. Then is equal to BC, a column vector, B below that C, and then a 2 cross 2 matrix, variance of x, covariance of xz, covariance of xz, variance of z. So you multiply these two matrices, you will get the first two equations. Right? Sure? This big square matrix is called a variance covariance matrix. Yeah? This whole thing is called a variance covariance matrix. Right? Okay? And think of this. If covariance zy, suppose I multiply all sides. Okay? I multiply everything throughout by 1 upon sigma x sigma y. What will I get? So if I divide covariance of xz, covariance of, for example, if I divide the covariance, or if I divide all the terms from the variance covariance matrix by sigma x sigma z, what will I get? If I divide all terms in the variance covariance matrix by sigma x sigma z, the first term in the variance covariance matrix is variance of x, right, divided by sigma x sigma z. So I'll get variance of x divided by standard deviation x will cancel. So I'll get sigma x upon sigma y. First row, first column will be sigma x upon sigma y. What will be the first row, second column be? Covariance of xz divided by sigma x sigma z. 1. That will be a correlation between xz. So I'll write it as correlation between xz. Second row, first column will also be correlation between xz. Yeah? And the last row, last column will again be sigma z, variance of z upon sigma x sigma z. So variance of z, so sigma z upon sigma x. Sigma z upon sigma x. Right? Now the problem is, you will realize that if x and z are perfectly correlated, then this diagonal term will be 1, this diagonal term will be 1. Yeah? And that matrix is not invertible. So you will not get a solution. Right? Okay? So if you have perfectly correlated variables, you don't get a solution. Right? Why don't you get a solution? Because now, look at this equation, right? So for example, I have these two equations here. So I have this equation and I have this equation, right? Okay? Now, so from this what do I have? B, covariance xz is equal to covariance zy minus C variance z, right? This equation can be converted into this equation. Very simple, no? I have taken this term on this side. So I have, interestingly now, so from this it follows that B is equal to covariance zy upon covariance xz, right? Okay, so basically B covariance xz is equal to covariance zy minus C variance z, right? Okay, so let me divide throughout by okay, right. So let me divide throughout by variance z. Okay, so I get B, or let me see if I want to see what is the relationship between, say, so I've got this right. Let me check. Covariance xy is B variance of, oh yeah. So covariance zy, B, no sorry, this should be variance of, I'm sorry, I just need to, yeah, it should be like this, yeah. You see I made a small mistake here. Because the first term, I'm sorry, I did a typing mistake. So the first term, from the first term you have covariance of, I'm so sorry, covariance of xy is equal to covariance. So basically B variance of x, right, plus C covariance of xz, right? That's the first term. Here, if I open this out, no? It will be covariance of x with A, which is 0, plus B variance of x, plus C into covariance xz, plus covariance xe, and covariance x is 0, right? So you get this term, right? Similarly, covariance of zy will be what? Tell me. Can you tell me what will be covariance of zy? B, perfect, covariance of xz plus variance of z, right? Sure, now all these covariances can be calculated numerically from the data. So you will have two equations and two unknowns. Now let's explore B, right? So I have B covariance of xz is equal to covariance of zy minus C variance of z, right? Sure? Okay. Now, right? Okay? Sure. So covariance of zy is C variance of z, covariance xz plus C variance z, right? Okay. It will be easier, it will be more insightful if I try to find C, because C will give you better understanding from this equation. So C variance of z, right? Okay, because C is really what I want to talk to you about. C is equal to, so I get, what will be C variance of z? Covariance zy minus B covariance xz, correct? Sure? So what will C be equal to now? C will be equal to covariance zy upon variance of z, right, minus B covariance of xz upon variance of z, right? Sure? Now do you recognize this term? Covariance zy upon variance of z will be what? Yeah? Just recognize this first term. All familiar terms now. What is the first term? So if you have just one single variable regression, where y were the dependent variable and z were the independent variable, what will be the formula for the coefficient of z? Just like when we have y and x, y is the dependent variable, z is the independent variable, what gives you the coefficient of z? Covariance of yx upon the variance of x, right? if you are just one regression, y is equal to a plus a bx plus e, then what is the formula for b? Covariance of xy upon the variance of x. Now, if you are just one regression, where y was the dependent variable and z was the independent variable, then do you recognize this first term? What is covariance of zy upon variance of z? It is a coefficient on z in a regression of z on y where z is the only independent variable. So for example, if y is equal to dz plus e, this will be d, right? Covariance of zy upon the variance of z, that will be d, right? So that is nothing but the coefficient you would get if you regressed y only on z. But x is also involved, right? Do you now recognize the last term, variance xz upon the variance of z? What is that term? If you had just one regression where x was the dependent variable and z was the independent variable, then that is that coefficient. Right? You see the point? Yeah? Everybody sees this? Why is this important? Because now what is C? C is supposed to be the impact of Z on Y. Yeah? Okay? C is supposed to be the impact of Z on Y, right? Okay? So interpret this equation for me now. If C is supposed to be the impact of Z on Y, keeping x constant, right? It's a partial derivative, no? Yeah? It's a partial derivative. It's dy by dabba y by dabba z. That's C. What do you mean by keeping x constant? You're not allowing x to move, right? The impact of y, impact of z on y, keeping everything else constant. Think of this and tell me what is this term then trying to tell you. So it says, if z changes, y changes because of two reasons. One is of course this direct impact, right? Okay, but because z is correlated with x, or might be correlated with x, as z changes, x also changes and it has its own impact on y. So z affects y directly, but when z changes, x also changes and that has an impact on y. Right? So when you want to get the impact, the partial derivative of z on y, keeping everything else, you have to separate out the two impacts. Okay? So what is this first impact? The first impact is the direct impact. From which what do you have to separate out? The impact on y that is happening through z, x's impact on z. So this last term really is the impact of z on x. And this is the impact of x on y. So this says, okay, what does this impact measure? This impact measures a product of two things. Z changes, so x changes, and because x changes, y changes. Whereas this part measures the total impact of z on y. So it says C is the total impact of z on y minus the indirect impact of z on y. That is why it's a partial derivative. Yeah? When will the two results be the same? When will the impact of B, when will it be the case that whether you include Z or not, whether you include X or not in the regression will not matter for the impact on, for the coefficient of Z? When will it be the case that whether you run a single regression, Y is equal to A plus BZ, or if you include X in it, the coefficient of Z will remain the same? When will that happen? Yeah, two things. When one is B is 0, that means that X does not impact Y. So Z impacts Y directly, Z impacts X, but X does not impact Y, in which case the coefficients will remain the same. Or when Z changes, X does not change at all. The covariance is 0, which both cases will not necessarily be true in most cases. So when you include additional explanatory variables, the coefficients of the existing variables change. Right? Now that opens a big problem for us, because you can't look at a variable in isolation in a regression model. It's a whole group of relationships which you have to capture correctly. And how do you know? Right? For instance, I want to model the market share of Hindustan Levers, because I have spent a lot of time trying to do that with those Hindustan Levers people, right? So market share for, what do typically market analysts do? They try and do, so there's a trial and error, right? You keep on adding variables, you keep on dropping variables, right? Okay? But remember, every time you keep on and you look at whether that coefficient is significant or not, right? So you put y is equal to a plus bx, right? And then you put a z, and you see whether z is significant or not. If z is not significant, but there's a lot you're doing to this coefficient here, right? Okay? So even when z is included, z is not significant, right? And if you conclude that because it is not significant, I accept the null hypothesis that it does not have any impact, which you have no business to do, you're still changing the coefficient here. Right? Okay? So how do you do that? Yeah? Many times what people try to do is they try to model the R square and try to get a model which has the highest R square and all that, right? Okay? But there are also other ways which are looking at various information criteria for it. Right? There's something called the Ekaiki information criterion, which is very similar to an R square. Right? But the lower the R square, you'll be very unhappy. But lower the AIC, the better. Right? And we will talk about that. Then there are ways of stepwise regression methods, where you actually try various things and get things, right? Okay? But all of them have the problem of you can't add and subtract variables suppose, for example, there is a variable which you put in the regression model. Yeah? And that variable you find is not statistically significant, you drop it. But what if that variable is correlated with an included variable? Then your regression has gone for a toss. Right? So all those kinds of problems is what we'll now learn to deal with. Right? Because regressions are very easy to do on a blackboard. But with real life data, to reach really robust conclusions, you have to really, it's more an art than you really have to have experience of doing it over and over again and getting the right kind of regressions. Right? And they're so hard to do that it's very easy to throw any regression out of the window. Right? So if in a conference I didn't really like a person, I can very easily keep on picking holes, right? No, what you're doing is nonsense, right? This is, right? Sure. So you see this point? Okay? Right? And we learned how, for example, if basically if your x is correlated with the error term, z is correlated with the error term, then none of these equations are there. They are not valid equations. And if they are not valid equations, then you can't do the regression. So formulas are derived on the basis of wrong assumptions. Yeah? And the point is that the error term is unobserved, right? So I can never know what is the correlation between z and e, x and e. So I can adjust it here as well. Right? Okay? Sure? But assuming that the x terms and the error terms are uncorrelated, beta hat is covariance of x upon covariance of xy by variance of x. We know that the sample size becomes large because the covariance is a mean, the variance is a mean. Both those means will go to their population values. So I know that as the sample size increases, my sample means will get closer and closer to the population means. So my beta hat, the sample regression model, will get closer and closer to the population value. And we saw that last time, right? As you increase the sample size, your variance estimators become better and so on and so forth, right? Okay. We also know that because the deviations around the mean are 0, right? And the mean the sample mean is an unbiased estimator of the population mean. Even if a small sample, if you keep on taking repeated samples, random samples and form the sample mean, then each sample mean will be different from the population mean, but the average of all sample means will be the same as the population means, because the errors will on an average get to 0. Right? We have actually looked at. And we know that covariance is a mean, the variance is a mean. So both those means have that property, and therefore we also can say that the OLS estimators will be unbiased and consistent, but provided the formula is correct. If the formula is not correct, they are not unbiased and consistent, right? And I'll now show you what happens if the formula is not correct. We'll do some similar. Last time we learned 2-3 things. One, we learned that as the sample size increases, our variance estimates become more and more accurate, our sample size, our coefficient estimates become more and more accurate, right? That is the consistency part, right? Because we saw actually that the variance of our beta hat, it was a ratio. What did you have in the numerator? Variance of the error term divided by n. What did you have in the denominator? Variance of x, right? We realized that the variance of x was actually information. Because more is the variability in x, the greater is the reliability in saying how y changes with x. Even if you have 500 values of x and all are the same, then I don't have any information on saying if x changes, how much y changes. If 499 values of x are the same and only one value changes, then out of 500 I have seen only one instance which tells me how much y changes with x. So my effective degrees of freedom are 1. I have only one bit of information which is valuable, right? The greater the variance of x, the better is our estimate, so lower is the variance of the error term. Variance of beta, right? The more precise is our estimate, because there is a lot more variability in x, right? Sure? Is this idea clear? And that's very common for the inference, no? Suppose I want to find out, if I am interested in understanding how much additional expenditure does a household have on education if the household's income increases by 1 rupee. And if all the households in my data have the same income, then I have no information in the data. If I have households with various different levels of income and I record their expenditure, then I have more information. So variance of x is really information. Similarly, number of data points is also information. Yeah? As n increases, I have more information. So my guess is more accurate. Whereas sigma square is the reason why y varies for reasons other than x. There are all these individual level hetero. So if there is the most variation in children's weights is caused by a lot of other things apart from their age, then obviously my ability to say how much weight changes, average weight changes with age, is relatively low. But if the major driver of weights is age, and everything else is relatively small varying, right? So the change in y because of everything else is relatively small. So the variance of the error term is small, then sigma square is small. And so variance of beta hat is low. My estimates are more accurate, right? So n is information, sigma square is information. So I like to look at it this way. I rewrite this formula. I take 1 upon sigma square out and then find the ratio sigma square upon n. So I write this as 1 upon sigma square into sigma square upon n, which is the same thing. Sigma square n divided by sigma square x, which is sigma square n into 1 upon sigma square upon n into 1 upon sigma square x. So I think of sigma square, variance of the error term, as the noise, right? N as the information, right? But this is just n is not useful to me if variance of the error term if variance of x is small. If the variance of x is small, 1 upon sigma square will be large. Right, so 1 upon sigma square into sigma square upon n gives me how much uncertainty there is in my estimates. Yeah? Right, so that should be a measure of uncertainty. And you see now intuitively why that would be the case, right? Sure? Is this clear? Okay, so now we'll see what happens if I omit if I omit an important explanatory variable. We'll do some simulations, okay? Right, and then so I'll need 2 libraries for that. Yeah? So I'm going to say X is our norm, say 100 observations, right? Sure? Z is a variable which is derived from X, but not perfectly correlated to X, right? So Z is a variable, so R norm is just 100 random numbers. So X is 100 random numbers, normally distributed, mean 0, standard deviation 1. Z is correlated with X, yeah? Right? 0.3x plus R norm 100, okay? Right, folks? Okay, then I have y which is equal to 2 plus 3x plus 2z, right? Okay? थोड़ा unclear है करे थे. It's a little bit hazy today, no? Can we wipe the lens? Is that clear? तेरा स्विच ऑफ करो, स्विच ऑन करने का. रिबूट कर, रिबूट. It has got some AI system where it reads that and then tries to focus all that. Because there is no focusing button in that as a result. हे इथे पण ऍडजस्ट करत आहे. हा ते स्वतःच करतो फोकस. द अँगल एक्सीड्स 15% काहीतरी म्हणला तो. बघ जरा आता परत कनेक्टेड टू द little better, no? Yeah? Okay. Right? R norm, right? Okay. Ata, what do we have to do now? We have to run this regression 10,000 times. It's a simulation, no? So what we are going to do? We are going to run this regression, but I am going to omit Z now in the regression. Right? I want to do just y is equal to a plus bx. Z I am not using. Right? What is the y, and I'm going to look at the distribution of the coefficients of x. Yeah? What is the true value for the coefficient of x? 3. Population value is 3. So if my estimators are still unbiased, I should get the sampling distribution of the coefficient of x, which should have some variability, but the mean value of that should still be 3. Right? So I'm going to empirically try whether that is true. Right? Okay. And for that I need to calculate many estimates. Right? So I'm going to take a repeated sample of say size 30. Right? So first I'm going to say some number vec, okay, C rep 0. I'm going to get 10,000 replications. Right? Yeah. नहीं दिसत है? दिसत नहीं है? अच्छा, स्क्रीन शेअर केलं नाही आहे?
So please, yeah, screen is not being shared.
Yeah, because we. Can you see the screen now?
Yes.
Yeah, so I've just generated a random number x 100 normal values, y actually, and then z which is correlated with x because z is 0.3x into r norm 100, and y is equal to 2 plus 3x plus 2z plus a random error term. I'm going to do a regression where I'm going to omit z even when z and x are correlated, right? I'm going to see the impact on what happens to me, right? Okay. So data is equal to sample understroke n, right? I have to take, so okay, so I have to put everything here in the data frame. Yeah? Okay? I'm now going to do a regression. I'm going to take a sample of size, the data of size 30, right? So if I just run this, if I run this up to here, and if I now just run this, we have to run dplyr also. Hey. Yes, if I take data now, a random sample of size 30 is generated, right? 30 data points, a random sample is generated, right? Then I'm going to do model is equal to linear model, y regressed only on x, and data is to be taken from this data set called data. Yeah? And then I have to take the beta coefficient from there, right? So, and put it in the vector I. Coef model 2, and you do I is equal to I plus 1 if I greater than 10,000, break, and then this bracket, right? So if you want to see the whole code, you have to see it like this. Yes, everyone understand what's happening here? So I'm taking a sample of size 30, right? Rows, same rows, right? Because I can take arbitrary rows and, I can take one value of y from somewhere, another value of x from somewhere, that will belong to the same observation. So I'm now taking 30 rows at random. I can just take some x because they'll be unrelated, no? I can't regress the consumption expenditure of Mr. Chowdhury on income of Mr. Patil, right? I have to take the same data. So I have to pick up rows at random. So I take this. And then I do a regression, but I exclude LMY. Sorry, this is not Y understroke, okay? This is Y tilde. Yeah? Regression, you do a tilde in the regression model. That wiggle worm. There's a worm, no, on top left-hand corner. Did this? Now, I give you a first, try to do something. Give me what you have to now do is, you now know how to do this. Plot the probability density of VEC. Right? Now what will VEC contain after this is done 10,000 times? What will be the output? वेक में क्या होगा? What will be there in VEC? Any idea? Coefficients of X. 10,000 coefficients of X. Right? Everybody gets that? Sure? So now tell me whether coefficient of X is unbiased or not unbiased. Now you know how to do it. You know how to look at the probability density, how to plot the probability density of X, of the coefficient of X. Yeah? GG plot, geom understroke density, all that, right? And tell me whether it is, we have done this in the last class. You have done the geom density. So tell me whether, it's unbiased or what? Find out. If I is, because this, no? Okay, I is equal to 1. We have to VEC not found because my VEC is here. इसको नीचे ले जाओ ना. Okay, it will not work immediately, okay? It's not working for me. So there is a problem that you must find out. हो रहा है कि नहीं हो रहा है? Because you have to write repeat. Yeah? This is something that you have to do. If you want to write a loop, you have to tell the computer what to repeat, right? Yeah? and then plot the graph. So it should be like this. Is this running now? Huh?
Data equal to sample.
येते? Try कर. Try, solve this now. See, my city, yes, I'm also getting a constant, right? So it is not simulating, na? Let's try to see what the problem is. Yeah? I think R is आलं?
सर ते डेटा आहे ना आपण खाली लिहिलं रिपीट मध्ये
हां
त्याला वेगळं नाव देऊन डेटा इक्वल टू त्याचं वेगळं नाव
असं करू?
हां
ओके ते वरचंच तसंच घेत होतं. Hello, everybody's got these values? So if I do this now, let's get there. Let me just figure out why. Are you getting NS or are you getting all values? You are all getting all values? Yeah? 10,000 values, different values you've got. Now if you plot the probability, काय तू मायनस येते 3 0 म्हणजे मग तुझं रिप्लेस ना होत आहे. या हां Are you all getting different values? Last week we did the simulation. Please see the code. Yeah, I've got them now, right? Run the whole thing, you will get that, right? Now check whether the data or whether the estimates of beta hat are unbiased. First check, make sure everybody is getting 10,000 values of beta hat differently. नहीं था? ये क्या कर रहे हो?
ये पता नहीं आया, यही आया।
नहीं, अरे बाबू रिपीट है ना, इसको नीचे ले आओ, है ना? I is equal to 1 if I less than 10,000 repeat end data 30, right? Coef model 2. हो तो प्लॉट डेटा नहीं करना, उसको जीजी प्लॉट से करना पड़ेगा ना, ये तो प्लॉट करेगा। अभी देखो ये जीजी प्लॉट से तुमको अंडर जियोम अंडर स्ट्रोक डेंसिटी से डेंसिटी प्लॉट करना पड़ेगा ना। प्लॉट डेटा उनसे कैसे होगा वो, अभी रन करके देखो।
ये मैंने पहले किया था पर
हाँ, तो आपका बेसिकली ये प्लॉट डेटा कमांड नहीं आएगा ना, जियोम अंडर स्ट्रोक डेंसिटी आएगा तुम्हारा ना। इसको करने दो, हो गया, हो गया कि कर रहा है अभी, कर रहा है अभी। उसके बाद just see what data you have, then you have to use GG plot to do the density plot. प्लॉट डेटा तो बस XYZ प्लॉट करेगा ना, वो नहीं चाहिए हमको, उसको वेक का प्रोबेबिलिटी डिस्ट्रीब्यूशन चाहिए,
नंबर्स जब आ जाएंगे उसके बाद जीजी प्लॉट का
उसका डेंसिटी प्लॉट चाहिए ना। हो गया, हो गया। नाउ इफ यू से वेक आ रहा है ना अलग अलग, इसका डेंसिटी प्लॉट येतोय पूजा, आ गया? एव्हरीबडी गॉट दिस? काय झालं सांग मला? हा, तू वेक म्हणून टाईप केलंस का शेवटी? दाखव मला काय येतंय. Hello? Did you get that? Yes. Everybody's got that now? Everybody's got that? Am I now ready to tell you, are we ready to check whether the distribution of beta hat is unbiased? Right? Okay. So let's do that now. So first vec is equal to data dot frame. We have to call it into a data frame, right? Yeah, it has to be called into a data frame to do a GG plot. Then P is equal to GG plot vec, right? Plus geom understroke density AES x is equal to vec. Yeah? Right? This is my distribution of beta hat. Yeah? This is my distribution of the estimators of beta hat. What is the true value of beta?
3.
3. Is it centered? Is the mean value of beta at 3 here? No. Right? Okay? Sure? So the estimator is not unbiased. Right? And do it a little bit more colorful, no? Fill it with some color and all that, so looks nice. So first do some aesthetics with it, and then tell me what, is this a problem of the sample size then? Do you think this will become better if you increase the sample size?
No, because sample size will decrease the variation. But
She says sample size will decrease the variation, but
it won't change the mean.
she says she won't change the mean. Does anybody have a different view on this? What will happen? Can we solve this problem by increasing the sample size? Yeah? Okay, but what is the essential problem and why? So first try increasing the sample size. Increase sample size from 30 to say 100. You can do with replacement, so you can bootstrap any sample size, right? So try to increase the sample size from 30 to 100. See what happens. Arey, sorry. Yeah, increase the sample size from 30 to 100. Yeah, but is the bias gone? Thirty से 100 करोगे ना? Run it again and get this picture. Yeah? आता तुला कोड माहित असेल पाहिजे. You have the code, no? So you should know where to make the change. तिला विचारू दे. Find the code, know where to make the change. Where will you make the change? Sample understroke n, 30 to 100 करोगे. What will happen? Huh? Is it improved? Has the bias gone? वाढला ना? If the bias is not gone, right? Shows the sample size is not solving this problem. है ना? Yeah? Why? Why has increasing the sample size not helped us? Why is increasing the sample size not helping us? Socho, that's how you think like an econometrician. This is what econometrics is about. It's not just about putting data into computers. It is about thinking. क्यों नहीं हो रहा है? अच्छा, एक hint देता हूँ आपको. Go here, right? Here, and in this, instead of 2, put 0. Instead of put 0 and do this again. Instead of 2, put 0. And then do it again. Not here, sorry, here. Instead of 0.3, put 0, I'm sorry. Instead of 0.3, put a 0. I'm so sorry, change it here. In line 4, instead of 0.3, put 0. And see what happens. Instead of 0.3, just put a 0. What is the mean value now? Run it again properly. Run the whole thing again. You change the value and then run the whole code. So if I change this value to 0 and I run the whole code, नाही. Visually तुला दिसत असेल. So what you have to do is, once that's done, okay, huh? If I just do round, if I round it off to say 1 digit, if I now draw this, okay. If I just do it this now, if I just remove that x altogether and let z be just random numbers, eh? Okay, now suppose I add z in this regression equation, right? Okay, this will be a better hint, right? Though it should work really. Yeah? Sure? I just added z in the regression equation. Okay, if I actually did this simulation a larger number of times, say 100,000 times, then it'll actually be much more centered on z, on 3. Yeah? So, so tell me one thing now. When I put z in the equation, my estimators became unbiased. But when z was not in the equation, my estimates of beta were biased. Yeah? Why? And why was not adding, increasing the sample size helping with it? सोचो सोचो सोचो. एरर टर्म नॉर्मल नव्हती हा प्रॉब्लेम होता की दुसरा काय होता? Okay, so z went into the error term. And by design, what is x? Look at the code, what is x? X is related to z. So error term is related to x now. So the moment error term is related to x, the formula for beta that the computer is using is not a valid formula. Are you getting this point? Right? So increasing the sample size won't help because your formula is wrong. Yeah, look, you're trying to make orange juice, but you're using apples. How many ever apples you use, orange juice आएगा क्या? नहीं आएगा, उसके लिए दूसरा मेथड यूज करना पड़ेगा ना. Right? Okay? Sure? So the moment x and z are correlated, right? And the point is, So if you now, for example, remove z from the regression, so let my computer do it 1 lakh times just for this point, right? Okay. So when you think of a regression model, suppose I am trying to correlate, my regression model is I am trying to explain the academic performance of a child, right, as a function of the child's family income, okay, and the education of the mother, right? So how well a child performs in the 10th standard is a function in my regression model. It depends upon the family income of the child, right, and the education levels of the mother of the child. Will this regression produce unbiased coefficients? Will this regression produce unbiased coefficients?
No, because there are other factors which are impacting the child situation.
Yeah, but other factors by themselves don't have a problem, right? Other factors by themselves don't create bias. If they are related with an included variable, they create a bias, because once you don't take them into account, they go into the error term, and then because they are correlated with included variable, they create a problem. So what could be other factors which are correlated with an included variable? Included variables are family income and mother's education. What could be the other factors that are correlated with an included variable? Father's education could be one, right? What could it be correlated with? Mother's education, income, both, because the richer, probably better educated fathers might have also, the families might have better incomes, and more educated men would probably be marrying more educated women, so both will be correlated. Suppose I include father's education also. So this says that I must include father's education also in my questionnaire. Is that enough to give me unbiased coefficients? Could be other variables. Because ultimately we want to have unbiased coefficients, no unbiased estimators. Otherwise there is no whole point of that. Whole regression is invalid. What could be other factors that you need to really take account of? Whether child goes to a coaching class, but coaching class will probably be related to the child's income. Another variable which you need to take into account, otherwise regression होगा ही नहीं. और क्या करोगे इसमें?
So that will have like a lot of variables.
Yeah, so designing a good regression requires a lot of thinking. It is not just getting some data, whatever data you are putting it into, producing models with the best R square. Because R square कितना भी होगा, coefficients का मतलब नहीं है तो कुछ फायदा नहीं. The formula for R square also is not correct. Yeah? So what could be the other variables?
Elder brother or sister.
Siblings, education levels of the academic achievements of the elder brothers and the sisters. Okay. Those might affect, and those might again be correlated with mother's education or whatever, right?
Which school does the child?
Which school does the child go?
But that will be correlated with the income.
Yeah, that will correlate. If you didn't include that, then you will get the error term correlated and the regression hoga nahi. Yeah? So the most important point that I am trying to convey to you is, and why is it important? Because you're going to do a survey. Your survey has to have those questionnaire, has to have that data beforehand, no? So what data to collect will depend upon what variables have to be there, whether you want to avoid and you want to do. So if you decide to do a regression, then you must figure out you want to get coefficients of the regression. The coefficients of the regression should be unbiased, right? That is the minimum you want, minimum, right? If they are unbiased, then you have to make sure that there are no omitted variable biases. So if you want to avoid an omitted variable bias, you have to have data. Right? If that variable can be measured, if data exists on that variable, you have to have that. So you have to do a lot of thinking a priori. Right? Okay? Sure? So that's why you read literature in the past. Think, okay, other people have done regressions. What are the variables that they have used? Look at all those variables and say, oh, one of those variables is not there, which could create an omitted variable bias. Right? So you say, okay, I must now correct that. So then you include that. And then you write a fresh paper saying that all those results are invalid because they got an omitted variable bias, mine don't have. Okay. Sure? So that's how basically, but you need to think carefully. Okay? So let me now give an example. Suppose I'm trying to understand the labor force participation of domestic workers, family, domestic help workers. Right? And suppose my Y variable is the number of hours that a particular woman works. And the X variable is the family income of the woman. My argument is that women who are wealthier, so there is a U-shaped, this Claudia Goldin's very interesting thesis about women's labor force participation, right? As women's labor, as modernization happens, as men start working outside, family incomes go up, so women actually experience just the leisure effect, the income effect and not the substitution effect, so they reduce their work, right? That is Claudia Goldin. So you want to test this. So you want to argue that as income levels goes up, women's labor force participation will initially fall and then rise. So your X variable is you've done a survey of many women who work as domestic help, and each woman you have asked how many hours on a day you work, and then you also have estimates of the family income. So X is the dependent variable, income is the number of hours worked is the dependent variable and income is the independent variable. Do you think this regression can be done?
There are other factors.
No, let's just focus on this. Other factors, of course. What are the other factors? But there is, before you think of other factors, I see an immediate problem here. What is the dependent variable here?
Number of hours.
What is the independent variable? Income. Right? So obviously, our hypothesis is that the number of hours worked are determined by income. But isn't income determined by the number of hours we work? Right? So Y depends on X, X depends on Y. I immediately have endogeneity. Same problem. X and E get correlated. So ये regression भी होगा नहीं. Plus there might be other reasons. Other omitted variable biases can be there. Remember, it's just not any variable is omitted, right? It has to be a variable which is correlated with an included variable. Yeah? So like for example, now I've run my regression 1 lakh times. So if I do a P now it's 3, right? It's still 3, right? It's still a little bit here and there, but still 3. Yeah? Okay, it's a nice centered around 3. Yeah, and if I do round mean, yeah, so it's a simulation, so it's very close to 3, right? Sure? If I want to just round it off to 0, just the number 3, right? Okay, sure. So now, let me prove this point to you. So now I have Z, which is an important variable, right? I've got X, I've got Z, right? And X and Z are independent of each other, right? X and Z are independent of each other, right? I have a regression which does not include So I have a regression which does not include Z. I have just X. Right? Let's first do it in a smaller scale. Alright, so let me just do it on a smaller scale first. Yeah, so now in my regression model, I don't include Z. Z is not correlated with X. Okay. Yes, if I now do round, vec round, mean, vec dollar vec, and I want to round it off to 0, I get 3. Right? Because it's a simulation. So some little 3 around 3.01 वगैरह कुछ होगा. Sure? Okay. So I'm doing this, right? Because it's 2.99, then it will be 2 rounded off to, so pretty close to 3. Sure? Okay, now look at this. Now tell me, if I now remove Z from this regression, right? If I add Z to this equation now, right? If I add Z to this equation, tell me what happens. Now there is no omitted variable, the Z is not correlated, so there is no problem of bias. So if I omit a variable which is not correlated with X, there is no problem. Or is it true? Now just look at this spread and put Z in the regression and see how the two coefficients of beta change. Put Z in the regression. Put Z in the regression and tell me what happens. क्या हुआ? No change? Spread? Spread decreased, no? The spread has decreased? Sorry. The spread has decreased? Right? Why has the spread decreased? If I include a variable, so what it means is that if I exclude a variable which is not correlated with X, my estimators are still unbiased, but their inaccuracy is high. Right? The spread of estimators is high. Once you included Z, the spread came down. क्या हुआ? Logic क्या है इसमें? So basically, Y depends upon X and Z and E. If you don't include Z, then Z gets included in the error term in the regression model. So the variance of the error term is the variance of the error term itself plus the variance of Z. So the sigma square E in the denominator becomes bigger. So the estimators become more spread out. Yeah? Okay? Sure, so the variance of beta hat will go up. Right? The variance of beta hat will go up. So the inaccuracy in the estimate of the included variable will increase. Why? Because y is changing because of x changes and z changes. You are not observing the change in z. So your ability to say how y changes with x is worse off than when you also observe the changes in z. Yeah, so if you wanted to, for example, understand how a child's educational level changes with the educational attainments of the mother, then you must have a situation where father's education attainments are not changing. You'll have to take children who have the same father's educational attainment, have different levels of educational attainment from others, and then you're able to see how mother's education levels impact the child's education, right? So you have to control for the father's level of education. That is exactly what the including Z in the regression model does, like we saw in that coefficient. Right? Is this clear? So there are two things, right? One is if you omit a variable, it may or may not bias the regression results. It will bias it if it is correlated with an included variable. If it is not correlated with included variable, you will still suffer. But the sufferance will be in terms of inaccuracy and not bias. Inconsistency. Yeah? So we'll take a small break now and come back in 15-20 minutes, right? And then we'll think of, do some actual regressions, and then you realize how hard it is really. Yeah? And then I'll first do one small regression, explain to you basic concepts. See, what happens is, the problem with this is that all of you do t-tests for regression, no? If you are into testing for the significance of beta hat, what do? Beta hat divided by the standard error of beta hat. That is a t-value. Now if you omitted a variable, standard error of beta hat are going to be large. And therefore the t-value is going to be small. Because beta hat upon the standard error of beta. Larger standard error means lower value of t, which will mean that beta x might turn out to be, you might think x is not significant. And therefore you should drop it. No, that's not the way to go about it, right? It's probably because there are other variables you want to put in the regression, right? Or you don't have enough data points, right? So even the decision to actually drop a variable from the regression model has to be taken with a lot of care. You just can't look at those significance levels and drop variables, right? Sure, so let's, on this important note, let's break for tea. So I'm going to open a new file, and I want you to install a library called Wooldridge. Install packages, so we are going to install a package called Wooldridge. Right? So there is a textbook, very famous, very popular, excellent textbook by Wooldridge on econometrics. And this is all the data sets from Wooldridge's book. So you can actually do the exercises. Right? So a package called Wooldridge. Right? Yeah? Wooldridge. So install that package. So now library, Bullrich.
So your screen is not visible.
Yeah, I'm just sharing, Pallavi.
Okay, sir.
Yeah. Visible now?
Yes, yes.
Okay. So data H price 3. Okay. Data H price 3. Okay. Understand what this data set is. So if you say help H price 3, you'll be able to read what the data is about. Help, if you go to the console here and say okay, if you say H price 3, so basically 321 observations on 19 variables. So it's data for 2 years, 1978, 1981. Then we have basically house prices, and data on age of the house, then age square, right? Then the kind of neighborhood, right? And what those neighborhoods are, we'll see. Neighborhood 1, 2, 3, 4, 5, 6. There are some codes for the. Then distance to central bus station, distance to interstate, right? The natural log of the distance, selling price, rooms in houses, square footage of the house, number of bathrooms, right? There's an incinerator, so there is something kachra burning depot, and the distance from that kachra burning depot, right? Right? The original exercise of this was to find out whether building a kachra burning incinerator reduces the housing prices. Right? That was the kind of a thing that they wanted. It is a kind of a panel data, but we're not going to look at it that way right now, right? Maybe 1 or 2 lectures later, when we deal with endogeneity and omitted variable bias, we'll immediately get into panel data, right? But first I wanted to get, because panel data is one way of dealing with omitted variables. Right, so for instance, if your marks are determined by how hard you study and what is your attitude to academics. Your attitude to academics I can't measure, right? But obviously correlated with how hard you study. So if I just have a marks on how hard you study, your attitude to studies is not there, right? Sure? So there, I don't have data on that, but it's correlated with how hard you study. So there is an omitted variable bias. So I have a problem. But suppose I collect data on your marks in your 8th standard and 9th standard. So I have data on what marks you got in the 8th standard, what marks you got, how hard you studied in the 8th standard, and there is an unobserved attitude, right? And then you have I have the same thing for the 9th standard. Your marks in the 9th standard exam, how hard you studied, and then which I have data on, and the unobserved attitude, right? So on the same person I have data for 2. This is a panel data. So what I do is, suppose I try to look at it this way. I say so I'm not going to look at what is the marks you scored in the determinants of the marks you scored in the 8th standard, but I'm going to look at the determinants of the change. So did you get more marks in the 9th standard because you studied harder in the 9th standard compared to 8th standard? Right? In that model, your attitude won't change because attitude was fixed in 8th standard and attitude was fixed in the 9th standard. You're the same person. So if I take the differences, the difference between the two, the difference between your marks in the 9th standard are determined by how hard you studied in the 9th standard and your attitude. Your marks in the 8th standard are determined by how hard you studied and your attitude. So the difference in your marks from the 9th to the 8th standard is determined by the difference in how hard you worked from the 9th standard compared to the 8th standard, and your attitude in the 9th standard compared to 8th standard. We are assuming that the attitude will not change, so that part will not be there anymore. This is called a fixed effect. Right? Okay, so unmeasured variables can somehow be dealt with panel data. Its panel data is cross-section data on the same individuals repeated in time. Right, so if I took temperatures, blood pressures of all of you today and blood pressures of all of you next Sunday, I'll have panel data. If I only took blood pressure of one person over the years, I'll have time series data. And if I just took the blood pressure of all of you just today, I have cross-section data. Though I have no reason to take blood pressure for any of you. Right? Okay. And especially I have no interest in raising it for some reason. Right? But yeah. So what we're going to do is, so you have area, log of, etc. We want to find out what are the determinants of the house prices in the year 1978. Yeah, this is data on 1978, right? Okay? So first thing that we want to do is HP 78 is subset, yeah? H price 3 year is equal to 2, right? Okay? Right, so year 1917, age of the household, age square, etc., etc. Yeah? Distance to the central business district, area of the house, land size, right?
Sir, are you creating a cross-sectional version of the same data?
Yeah, I'm just looking at the cross section of 1978. Then we'll see how we can solve the problem, because here the problem is house prices might depend on incinerator location, but incinerator locations will also depend on what house prices are, no? If the government, if Pune Municipal Corporation wants to start an incinerator which stinks a lot, it's not going to put it in Bandarkar Road, right? Because house prices here are very valuable. It's going to put it somewhere far off where nobody buys that land, right? So where incinerator will also be, so again you have Y determines X and X determines Y. So you have endogeneity. So OLS will not work. That's why I'm looking at a cross section 1970 just to get you sense of, right? When there was no incinerator, nothing. So there is no endogeneity here. Right? Okay. Sure? Okay, now, first let's just look at the simple thing, right? So what do you think should be the first important variable that would determine house prices? So we model building time pass karenge. Slowly, slowly. So rooms in the house, she thinks will be one determinant. Area of the house. So let's first start simply with area, right? So let's first let's do a simple basic plot. Okay? Or let's do a more fancy plot. Chalo. GG plot plus geom understroke point X is equal to area, Y is equal to, what is the housing price? What is the variable for house selling price? In the data, check. Price. Okay, so let's see how the regression looks. First let's look at how the scatter looks like. So there seems to be a positive relationship, right? Yeah, as area goes up, housing prices go up. Right? Yeah? Okay, now instead of housing area, suppose I took the age of the house. Okay. So it seems to be a very funny picture, no? So what is the relationship between price and age? U-shaped, right? Why is it a U-shaped variable?
Is it like a non-linear kind of relationship?
Yeah, but why, Pallavi?
Because very new houses are also not.
So as households age, their value declines. But when they really become 200, 300-year-old vadas, then they get antique values, right? Yeah, then you don't want to sell them. Then they become very valuable. Yeah? Sure? They become very valuable. This is a U-shaped thing. So it's often a U-shaped thing. What do? You include the variable area and you also include the square of the variable. Because the relationship is non-linear. Right? So again, my habit of doing mathematics mentally, if y is equal to a plus bx, dy by dx is just a. Right? But if y is equal to a plus bx plus cx square, what is dy by dx? A will not be there, b plus 2cx. dy by dx will be b plus 2cx. So dy by dx will depend upon x. So the slope of y with respect to x will be a function of x now. And this is what it is, no? For different values of x, the function is different. Yeah? Right? Getting this? So I put a square. So now let's build a simple model to start with, saying that model is equal to LM. Price is the dependent variable. Yeah? And first I said area we have to add plus age plus there is a variable called age square in this, what they've called something? Age SQ. And data is equal to HP 78. Correct? So it's LM, okay, linear model. And summary LM, summary model, sorry, what am I doing? So run this and you get the results of the regression. Yeah? So equal to A plus B area plus C age plus D age square. Our regression is y is equal to A, which is the intercept, plus B into the area, plus C into the age, plus D into the age square. Right? Sure? Everybody got this? Okay. So the estimates that you're seeing are the estimates of the ABCDs there. Okay? Right? They're the estimates of the ABCDs. Then the standard errors you see are the estimates of the variances of those. Yeah? Like each estimator, when we did it in our pictures, no? Each estimator had a spread. Right? So it is the estimate of that spread. Right? It's basically the standard deviation of that estimator. What is the t-value? We are testing the null hypothesis where the coefficient of area is equal to 0. You learnt when we did the basic t-test that when you want to test whether the sample mean, the null hypothesis sample mean is equal to 0, That's x bar minus mu upon the standard deviation of x bar, mu is 0. So it would be x bar upon the standard deviation of x bar, right? Sigma by root n. Sure? So this essentially is the null hypothesis that the area coefficient is equal to 0. So therefore it becomes 28.4031 minus 0 upon the standard error. The standard error is 2.6324. So just write 28 upon 28.4031 divided by 2.6324 will give you exactly 10.790. So if you want to test the null hypothesis that the area coefficient is equal to 30, what will you do? 28.4031 minus 30 upon the standard error. Whatever t value you get. Right? Here implicitly we are testing the null hypothesis that population value is 0, but that doesn't prevent you from testing any other hypothesis on the basis of this data. Right?
But sir, will that, I think, depending on what values we are considering.
Yeah, so what is your, it depends on what is your null hypothesis in your mind. Right, so you might, for example, want to feel that every time area goes up by 1 square foot, property prices go up by 30 rupees per square foot. In which case you will do this regression at 28.4031 minus 30 point something divided by the standard error. Sure? So it's very important to think like that, because what you typically do is, most econometricians would look at this and say, okay, the t value is very large. The null hypothesis is that the coefficient is equal to 0. Right? What is the test statistic? T value. Essentially, we don't know the population variance, so we put the sample variance, which is calculated here. You get the t value, and the p value of that hypothesis is very small, 0.0003, so you reject the null hypothesis. Right? Okay? Sure? And if you don't find that p value to be very large, you might not reject the null hypothesis. Okay? Sure? Now, there is another null hypothesis that you can reject. Right? For example, if I say my null hypothesis is that the coefficient of area is 100, 28 minus 100 divided by 2 will still be a very large number. I will also reject that null hypothesis. So there are many null hypotheses which I can reject. Right? But will it be right for me to then say, okay, right, okay, that value is not equal to, so basically just dropping a variable on the basis of, finding it to be statistically insignificant is not really a very safe thing to do. Right? Okay, fine. So everybody understands these output completely? Sure?
I'm having some problem in the codes actually. I'm not getting.
Not getting? So I'll show you the code, Pallavi. Yeah. Yeah, I'll explain to you. So, are you now running this? Is this running, Pallavi?
So yes, I am getting the output, but I am having some problem in this plot. I am not getting that graph. So it is showing as null.
Have you written this?
Yeah.
Age, price, ggplot, HP 78.
Yes, I have done this.
Okay. So now, so what did it say? Okay. The age coefficient now is first negative and then positive. right? So if you differentiated y with respect to age, you get dy by d age or d price by d age, or the slope of price with respect to age is minus 784.53 plus 3.68 into age. Right? So if you have a 100-year-old house, that would be 300 minus 784, etc. Right? But if you have a 700-year-old or a 1000-year-old house, then that would be 3689.3 minus 784, which will be positive. So if a house goes beyond 1000 years old, then actually with its age price increases. But for new houses, as they become older, prices fall. Yeah? Right? Okay? Then you have got to the F statistic. What is the F statistic? The F statistic that you have here is testing for the null hypothesis that area, age and age square, all of them are statistically significantly equal to 0. So how is it working out? The computer will do one regression only on the intercept, not including any of the variables. Then it will calculate the variance of the error term, the residuals of the regression. Right? Then it will do a regression with all the three variables. It will calculate the residual variance. If the residual variances are not different from each other, then including these three variables doesn't matter. So their coefficient must be equal to 0, all of them. But if the second variance is much lower than the first variance, yeah, then obviously you will say that these three variables matter as a group. How do you compare two variances, sample variances? F's test. Right? Sure? We did that, right? And that's why this is the F statistic at the end. Yeah. In fact, how is it done? It will say, okay, new variance. So in a regression model where you put all the coefficients equal to 0 is called the restricted regression. The one where you have not put all the coefficients equal to 0. So if you have a regression only with an intercept, where you implicitly assumed area, age and age square coefficients are 0, that's a restricted regression. The one where you don't have anything is unrestricted regression. Right? So restricted regression minus unrestricted regression, that is the change in the variance. Right? Change in the variance. Sure. And then that divided by the unrestricted regression. Right? Sure, that's how the test works. Therefore, if there are 100 data points, right, the restricted regression will be a regression with 99 data points because only constant is there. The unrestricted regression would be with 4 independent variables, so 96. So 96 minus 93 will be the 3 degrees of freedom in the numerator, and the denominator degrees of freedom will be 96 degrees of freedom. So therefore, it looks like this, right? 3 and 175 degrees of freedom in this case, right? And this is our beloved adjusted R square, which is basically the proportion of the data of the variance in Y explained by all the explanatory variables. But if you have more explanatory, does anyone know the difference between multiple R square and adjusted R square?
So I think in case of adjusted R square, if you are adding some redundant variables, it is going to go down.
Yeah, no. So it's like this, Pallavi. Okay, your multiple R square is just the fraction of the variance that is explained divided by the total variance. But if you add more variables, degrees of freedom are going down. So that estimate is relatively less reliable. Right? So therefore I have to penalize for the degrees of freedom. And so the multiple R square is the one, is the R square total variation in the data which is explained by our model, but penalized for the degrees of freedom that we are reducing now by putting more and more and more and more variables. Yeah? So this says, for example, about 56% of the variation in the data is explained. Yeah? Okay? Sure. So now,
So one more clarification.
yeah.
So like if you are adding like some more variables and without knowing that whether those variables are actually adding maximum model, so in that case the R square is definitely going to go up, but I think the adjusted R square.
Because the adjusted R square, because the degrees of freedom will go down, no? So the adjusted R square penalizes you for the reduction in the degrees of freedom. Right? So therefore, it imposes a cost on the model, because lower the degrees of freedom, lower is the reliability of your estimators. Because what is degree of freedom? The amount of independent information that you have to estimate a parameter. Right, so the degrees of freedom go down, your reliability is lower. Right, says okay, your R square is this, but really if you need to adjust it for its reliability, so if you adjust it, it becomes lower now. Yeah, so you take the pinch of salt out. Yeah, discount its credibility. Yeah, scale it down a little bit. Sure? Okay. So now you got this regression. Now try to improve on this regression. Now you know how to do this. Add variables, subtract variables, build a good regression for me. Right? And that's the task for the next 15-20 minutes. Try and fiddle with this, build a good regression, try to improve on this regression. Yeah? जरा खींचो खेलो थोड़ा सा टाइम पास करो.
Why did I keep age when I'm keeping means there?
Because, just a minute. Sure? Okay. Why? Because you see, the point is that the impact of age on price is non-linear. So initially as age goes up, price declines, but as age goes up a lot, price increases. Right? If you didn't include a square, if I just do y is equal to a plus bx, then dy by dx is just b. So the slope of the function doesn't depend upon x. Whereas if I add y is equal to a plus bx plus cx square, what is dy by dx? b plus 2cx, right? So if for example 2 is positive, c is positive and b is negative. So for low values of x, the slope will be negative. But as x increases, the slope will turn positive beyond the value of x. That's why the non-linearity. So if you are for example, if you want to model the earnings of a taxi driver as a function of the age of the taxi driver, how do you think the model should go? Or the years of experience, right? Inverted U, right? So as the taxi driver starts as a young man, slowly his age improves, he gets more experience, so his earnings go up. But beyond the point he gets very old, so he can't see properly, he tires early, he doesn't drive as long, so his earnings drop. So earnings is equal to b plus cx square. You would expect b to be positive, c to be negative. So initially for low levels of experience, as experience increases, your earnings increase. But if experience goes beyond a particular point, then your earnings will fall. Returns, so for example, for the impact of fertilizer yields on impact of fertilizer on sugarcane yields. If you initially add fertilizers to an unfertilized land, output will increase. But beyond the point, if you really saturate the land with urea and, and nitrogen and all that, then beyond the point, additional fertilizer will actually damage it. So you'll have a non-linear relationship. Right? So many relationships are non-linear like that, and that's why you use the square. अभी करो, अभी ढूंढो 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 अच्छा मॉडल बनाओ और मेरे को बताओ क्या बनाया आप लोग ने.
So typically before we start with the regression, is it good to always plot the data?
Plot the data, study the data, talk to the data, question the data, talk to, if you're a consultant, please talk to your clients, find out what they understand, talk, get your all domain knowledge that they have, figure out what they're trying to say. If you're building a model for tribals, please sit down with tribals, be friends with them, understand what they're saying, right? Then build a model. Right? So everything has to be done in a very immersive field level fashion. Unless you're a macroeconomist. Yeah? Which I think are not a great set of people to be, but there are all kinds of issues there, no? Because A, it's all non-existent, no? There's nothing called GDP. It's all physical, it's a paper, no? It's just a concept, it's not some physical reality out there. I don't really think that macroeconomics is even a science. Look, how can there be things? They're all conceptual, no? So what is GDP on paper is the data that are going to depend on some methods of computation and some assumptions about some missing variables and all that kind of a thing, no? So what is how can I really do econometrics on that? I've always worried about that. Aha.
Just human creation.
Yeah, but mathematics is some logical tightness and all that. GDP वो भी नहीं है. They value everything that's only sold on the market, right? Something for which a price. But now Google, I depend on Google for show me maps. This hour I am not paying even a single rupee. A huge amount of services being produced. Right? If you destroy all these Vetal Tekdi, then there will be a lot of things can be sold in the market. So you will get money. You show it in GDP, but that Vetal Tekdi destruction will actually not, people will become, you will lose a lot of things which are not sold on the market. So they will not be in the GDP. So I am always a little bit worried about all these things called. And that's okay to get an idea of the market, but put them in data and do some maths on that is a little difficult for me to follow. So play around with the data, find something.
I have taken this log of area as an additional regression.
But then Pallavi, you already have area, right?
Yeah.
So if you put log of area, they'll be perfectly correlated, no?
Oh yes, yes.
So you'll have a problem.
Oh, there's an area already.
Yes.
I will take this log of line probably.
Yeah, but then if you want, then log is a different scale, Pallavi, right? So the scales are different. Everything should be in the same scale. Log. So either you take everything in log or take nothing in log. Huh? Because the scale should be the same, no?
Yeah, but I think in that cases, no, like if there is let's say a log linear model, we need to multiply this the coefficient by beta or something like that.
Yeah, but you have to do something else, right? You don't get this result straight away.
Yes, yes.
काय आलं? शो आज रेग्युलेशन्स करून घ्या, सो यू गेट द सेन्स ऑफ द सॉफ्टवेअर, देन विल डू.
हे बघितलं की रूम आणि बाथरूम्स
आता म्हणजे R² ड्रॉप झाला तुझा.
R² ड्रॉप नाही झालं.
I am explaining 56% of the variation. Your model is only explaining 41% of the variation. So why not also include age and other variables? ते पण असू दे ना, ते jointly determine.
मिनिमम म्हणजे 50% तरी केलं.
असं काय नाही, जेवढं होईल तेवढं. बट आयडियली you should try and not minimize your R² and you should get a sensible model. So age is important for households, you should not drop it. Area is important for, once you go and start to buy a property, first thing you will inquire kitna room hai, kitna bada hai, right? What is the area? Area will have a higher price, so you don't drop it. Right? If you go to an old building which is almost come to redevelopment, you might not want to pay a lot for it. And there is no redevelopment plan, then you might not want to pay a lot for it, right? The new building you might want to pay more. So age matters, right? Then how far away it is from station might matter, might not matter, right? So check it. I would hate to have a house which is close to the station, but some people want to have a house which is close to a station. It's too noisy near a station, no? Yeah? I try to live always as far away from the city, any place as possible. But if you stay far off from the crowd, you have the choices with you to go into the crowd or not go into the crowd. But if you live in the crowded places, you have no choice. I live in Vahi and then I come to Pune whenever I want to. But if I lived in Pune, it will be hell for me. You know where to go. यूज नहीं है.
लँड ऍड केल्यावरती R² वाढतं.
पण कोएफिशिएंट्सचा सेन्स येतोय का? आर द कोएफिशिएंट्स रिमेनिंग द वे दे शुड बी?
Some variables are not continuous.
That's okay. That's okay. So what is the best model that you guys are getting?
Area, distance, age square, room and land.
Room and land. And what are the R squares that you're looking at, like?
Adjusted R square is 0.61.
So about 60% of this variation you can explain reasonably. Is everybody getting similar models? Huh? 0.62? 0.6162? What are the variables you're using?
I removed CBD.
You removed CBD.
So the thing is, when you add
61, 83 or 81. But when you remove CBD from that, it goes to 60.
Okay. But those are very marginal improvements, no? But is the CBD significant? And is the distance of INST also significant? They are significant, no? Then they matter. So you should keep them. Because what you are doing is now you are deleting an important variable.
And how is it explaining more then when you delete?
No, because if you, basically what happens is, if you are omitting an important explanatory variable which won't be correlated with other included variables, then just like the formula for beta is wrong, the formula for R square is also wrong. So the R square that you get doesn't make sense. Because the coefficients are biased, no? तो रिग्रेशन कोई मतलब नहीं है, कोई नंबर फंबर आएगा. See, what is R square? It is the error sum of squares upon total sum of squares. 1 minus. What is the error sum of squares? Y minus alpha hat minus beta hat x, which assumes that alpha hat and beta hat are correctly calculated. If they are not correctly calculated, then what you get is not the error sum of squares. So it doesn't make sense. Yeah? So just R square hunting at the cost of everything else is not a good practice. Yeah? Just getting the data to fit well. This is a problem with data science folks. They just want models which fit well. They've never taught omitted variables and all that. They just taught computer science and Python. That creates problems.
When you use both of them together, they are insignificant, both of them. But when you use them individually, they are significant.
Okay. Now he's saying that if you use both of them, they are insignificant. Right? But if you use only one, the coefficient is significant. Tell me what is the story, hidden story. Why are they insignificant? Because their t values are small. So it means that their variances are too high. Right? Okay?
They impact each other.
No. Yeah. So what it means is that if your y is equal to a plus b x plus c z, then the variance of b, beta hat, is not only sigma square n upon sigma square x. It's sigma square n, sigma square e divided by n, whole divided by sigma square x, the usual thing, plus 1 upon 1 minus r square, where r square is the coefficient of correlation between the two. Right? And if suppose that r square is 1, then 1 upon 1 minus 1 is not defined. So you will not get any variance. Larger the r square, smaller is 1 minus r square. So bigger is this variance, which is called a variance inflation factor. So if the two variables are correlated, their individual coefficient variations are going to be high. They'll still be unbiased, but the individual correlation will be high, and so the t values will look to be small. So the point is that in all probability the two variables are highly correlated. Can you check for their correlation?
Variables are technically the distance from the center of the bus district and the interstate highway. So the highway is far from the bus stand, and whichever you get close to, you get far away from the other.
Exactly. So both are correlated. Maybe negatively correlated. Can you find the correlation between the two? Just plot one against another. Just plot one against. You should always suspect a regression, okay? Computers are just give you whatever junk you put in, it will print out. It's for you to make sense.
Directly correlated. Positively correlated.
Highly, strongly, positively correlated? Yeah. Yeah. So that's why the variance inflation factors are large there. Right? क्यों हो रहा है ये? Because the theory says that look, y changing because of x and z. If every time x changes, z also changes a lot, then my ability to say how much y changes with x keeping z constant is very low, because z doesn't remain constant. Ideally, if I want to study the relationship between house price and distance from a highway, then I should be able to get a lot of cases where distance from the highway varies, but the distance from the interstate is the same. Only then will I be able to say how much distance from the highway itself on its own impacts house prices. Right? But if I don't have a lot of these cases, I have only a small number of cases where that can happen, it's effectively having a low N. So it's really having low degrees of freedom. That's why the variances become large. Right? This is a problem called multicollinearity. Right? And therefore a lot of data science people now use what are called lasso regressions or ridge regressions. They say, okay, we can't deal with this multicollinearity, so we are going to use, basically say, okay, little bit of variance bias is okay in our results as long as the variance goes down. Right? So that also we'll do soon. There are shrinkages, estimators and all those kinds of things. But the problem with data science people is they try to do these manipulations, that they'll not answer the basic questions of is the data good, is this the right variable to put in? That is what you have to think about. Economists think about that. Right? Are you guys getting this? Sure? Okay. Now next class we have to do instrumental variables. Problem is, जैसा problem होता है life में, अब इसको कैसा resolve करने का, instrumental variables and panel data. Two things we have to study in the next class. Those are very important things. Important for policy, everything. Right? And once you have got that right, the next 2-3 lectures we'll have on policy modeling and then we'll call it a day. So 4 or 5 more lectures we'll call it. Right? So that we also know how to, so basic idea is that at the end of it you should be able to do a regression properly, sensibly, understand in an understandable, in a way in which you fully understand what you're doing, not very mechanically. Would you go to a doctor who, when you go, sir, I have chest pain, bypass? No, you need people who will test you, examine you, try to see what's happening to you. They understand physiology, they understand medicine. You want to become econometricians like that. Yeah? Sure? So we will stop today and we'll come back next week. Okay, folks. Pallavi, any questions?
Sir, no questions, and I missed last class actually.
We are putting it up. Yeah? I'll put it up.